When we first started talking about derivatives, our definition of derivative was limit as h approaches 0. It was f of x plus h minus f of x over h. And graphically speaking, what we were talking about here was, yeah, if I start out at an x, and the x plus h, the h was just, it was just an amount that I went out from my x value there to get me a new x value. And so what this expression here described was, it was that taking that secant line slope, right? That's what it was. Well, ultimately what it amounted to was the slope. We were able to get the slope of the tangent line out of that. But another way we could describe this is, so this was what happened if I went out from the x a little bit. Okay, that's what basically the derivative gives me is what happens if I move out from the x a little bit. So that might be, if I change that input a little bit, what happens to my function? So that, and it ultimately winds up being the slope of the tangent. But well, so for two variable functions, z equals a function of x and y, derivatives get a little more complicated. Okay, because if you think about it, all right, so this was what for y equals f of x. We only had one input value there that we were changing a little bit. You see what I'm saying? Here, we've got two variables that we can change a little bit. So I could change the x a little bit, I could change the y a little bit. And so the derivatives are thus going to be a little more complicated. Well, it turns out what we're going to basically do is we're going to think about what are called partial derivatives, which a partial derivative is just going to be changing one of the variables a little bit at a time. Okay, so we're going to do what are called partial derivatives, and so that's what we're going to talk about in the next few moments or so. So partial derivative, that's just when we change one of the variables, input variables, a little bit. And the key, or one of the key things, is we're going to hold the other one fixed. That's, like I said, that's kind of key to this. You're changing one a little bit, but the other one is not changing at all. Even though both the x and y could change at the same time, partial derivatives, we're just changing one of them at a time. Okay? So here's our notation, or one of the notations. And, both of them, we're going to do a couple of them, like we did with our other regular derivatives. Here we said this could be dy over dx also. Well, here's the way, one way we will denote this. All right, so we've got function f, and the little x subscripted there, that tells me which one I'm doing the derivative with respect to. So in this case, I'm doing the partial derivative of f with respect to x. That's what that means. And so guess what? F, and then the subscript y, x, y, that's just our function notation, I guess, sort of thing. That's going to be the partial f with respect to y, okay? Now the other notation is It's kind of the Leibniz, but it's a little bit changed up because we are doing partial. It's kind of a modified Leibniz, I guess we could call it. Instead of a D, we're going to use this this little symbol here. It looks like kind of like a backwards 6. That's going to denote a partial. So this is another way to denote a partial of f with respect to x. And what it means, of course, is in this case we're changing x a little bit. And so when I do my, if you will, definition, Mark, just thinking a little bit, it's the x that's changing a little bit, all right? And so the x changes a little bit, so the f of x plus h, comma y, minus f of xy over h. So it's still the same basic definition. We're just doing, changing the x a little bit. So the h approaches 0 on the x's, if you will. So the partial of f with respect to y, same thing. It's the limit as h approaches 0. But in this case, we're changing the y's a little bit, so the f of x, comma, y plus h minus f of xy over h. So the y values change a little bit. So the x's are basically fixed there. Okay. All right, now, as far as what this means, as we know, the derivative means it's the slope of the tangent line, and that's basically what it means for partials as well. Just okay, so let's say I've got this little sheet, I don't know what you want to call it, kind of a, not a tangent, I mean not a plane, but kind of a little curved surface there. All right, and so when that's going to be my graph of the function, two variable function there. So the question is, what does it mean? If I do the partial of f with respect to x at a particular a, b point, what does that mean? Well, all right, so my x is a and my y is b, so let's kind of figure out where that is. It'll be up here. So I'm talking about somewhere on the curve. I don't know, I don't have a whole lot of perspective there, but it's somewhere on that curve figure. So what does this mean? Well, it's a tangent line, but there's a lot of different ways I could go tangentially off of that. Tangent just means you hit it at one point, right? You kind of skim the surface of it. Well, it turns out what it means is, all right, so let's say we cut this curve, so the y is fixed. So if I think about this curve, if I slice it at y equals b, so it kind of curves around like that. So that's how this surface is cut by the plane y equals b. So that's what we'll call C1 there. F of x AB is the slope then of that, or that tangent line, slope of that tangent line at C1 for C1. C1 curve, which is the curve that intersects the figure. With white was the white was the plane. Let's call it T1. All right. So guess what? If I do the partial of f with respect to y, I'm going to do basically the same basic curve here. Well, same A, B. So that point comes up here, some point P or whatever you want to call it. But partial depth with respect to y. The x is fixed. And so if you slice the curve, think about the plane coming up here at x equals a. So if we slice the curve like that, I'd probably get something like that. And so f of xy is going to be the slope of that, call it C2. It's the slope of that line. The slope of the tangent of that line. A lot going on here. So let's call that T2. So it's the slope of T2. So that kind of hopefully helps you a little bit understand what it is we're finding. We're finding the slope of a tangent line. It's just, there's so many tangent lines to that curve we can talk about. This is what the partial finds. The partial with respect to y finds that tangent line. Partial with respect to x finds that tangent line. The slope of that tangent line. So, anyway, the good news is the derivative rules all apply. We're fixing x or y, so that's going to be helpful. So let's do some. So f of xy equals x squared plus 3xy plus y minus 1. So let's find the first partial derivatives. Well, the first partial derivatives, that means find the partial of f with respect to x, and then find the partial of f with respect to y. They use the standard, I guess, function notation for this, or they use the partial. 6 1/2 dozen the other, I guess. Do what you want. Now, the key to this is, again, if I'm doing the partial with respect to x, the y is fixed, right? It's constant, in other words. And we know what we do with constants, right? The derivative of a constant is 0. So I'm doing the partial with respect to x, the y is fixed. So y is fixed, so keep that in mind. All right, well, that's still, that's just power rule, 2x. All right, so when we get partial with respect to x, when I get to the 3xy, the y is really there with the 3. 3 is constant, so is y. So really, the way I'm thinking this, for this one is 3y times x. Well, the derivative of x is just 1, so I've got 3y times 1. That's 3y. That's pretty nice if one of them's fixed. The product rule, you could do the product rule there, but y is fixed. The derivative of it is constant, you see, which would be 0. The derivative of constant is 0. So you don't have to use a product rule there. And then over here on these other, that's of course the derivative is 0, but again, y is constant. Derivative that's 0. That's it. That's the partial of f with respect to x. But there is a second one. We do have to do the same thing, but for the y. So this is the partial of f with respect to y. Well, when the y, doing the partial with respect to that, the x is fixed. So it is constant. And so that changes things a little bit. Of course, now the x is fixed, it's constant, so the derivative of that's 0. Now, for the partial of f with respect to y, I'm thinking that's 3x times y. The 3x is just a constant, so the derivative of that's just going to be 3x. Doing the partial with respect to y, so that's now something, it's 1. Derivative of that's 0, so 3x plus 1, that's going to be the partial of f with respect to y. So it's basically the same, just takes a little getting used to, right? Fixing those things up. Okay. Well, let's see. What about this one? F of xy equals y times sine xy. Well, you know the drill. Things can get complicated pretty quickly. This one's not too bad, I don't think, but let's see. So the partial of f with respect to x, xy, is the easy one. Easiest of the two of these because, yeah, the y is just a fixed number, so it's just a number, constant in front there, so I just need to do really the derivative of that, which, how am I going to do the derivative of that? What rule is going to apply there? Got the inside and outside, chain rule. Little chain rule there. So we got to do the derivative of the outside and the derivative of the inside. So the derivative of the outside is just sine, so the derivative of that's cosine. Inside stays the same. Then I have to do the derivative of the inside. Well, again, the y is fixed, so that's just a number times x. So the derivative of xy would be, with respect to x, be y, right? Everybody with me there? Y squared, then cosine xy. Question? Okay. What about the partial of y, then xy? Well, that's where we're holding the x fixed. So that's a little different story, isn't it? Because now I've got a y and then another thing with y. So that's going to be a little more complicated because I have to use what I have to use also here. I have to use chain rule again, but you got a y times another y thing. Product rule, right? I didn't have to use product rule here because when I was doing it with respect to x, this wasn't an x. This didn't have an x in it. So that was just a number. It's like a 5 there. But with respect to y, I've got use product rule. So it would be 1 times sine xy. That's the derivative with respect to y there. Plus then y times the derivative of sine x. Well, that's again our chain rule. Cosine xy. But now I'm doing the derivative with respect to y, so the x is fixed. So the derivative of xy would be x. Would be sine xy plus xy cosine xy. Okay. Question or concern? Okay. F of xy equals e to the x times ln x minus y squared. Yeah, so that's very similar. Partial here of x with respect to y. Sorry. Partial of f with respect to x. Start with that one. Well, this one's just the reverse of the last one, isn't it? Because this one I've got an x expression and then the ln of x and y expression. So it's just kind of the reverse of that. So the partial with respect to x, I might have to use the product rule on it. So the derivative of e to the x, I guess one of the reasons for doing this is just to review. What's the derivative of e to the x? E to the x, okay. Times ln of x minus y squared, leave that one alone. Then reverse that, so e to the x times the derivative of ln. Again, that's inside and outside. Derivative of ln is 1 over, leave the inside alone, times derivative of the inside. Well, I'm doing the derivative with respect to x, what's the derivative of the inside? What's the derivative of that inside? With respect to x. The y is fixed, that's just a number. Derivative of the inside is just 1, isn't it? Derivative with respect to x, I'm just doing the derivative of that. That's just 1. I don't know what I can do with that one. Is that all right? This would be right. E to the x over x minus y squared. So are we good with that? What about the partial with respect to y? Well, this one's the easier of the two because the first part is just an e to the x. That's just a number. So it just kind of comes along for the ride. Now I just have to do the derivative of that, which again, the ln, chain rule, so we do 1 over x minus y squared, right? Ln of x is 1 over x, so ln of x minus y squared would be 1 over x minus y squared, right? Then the derivative of the inside, well, now it's the y I'm doing, the x is fixed, with the derivative with respect to y, so times negative 2y. So, you know, it works about the same there. And you said you can maybe put these together and do that sort of thing. I don't like doing that one. Question or concern?